Hello everyone, welcome to a very long session of listening the before CCNA review. In this session, we are going to revise as far as we can all that I have completed, assembled the resource in my completion of CCNA. This is going to be a very long audio/video, and I am very thankful that you joined me here. And now, without further ado, let's start the session. So, this is not going to be a regular educational video in which I am going to express every topic as they come. This is going to be a comprehensive thing that I found interesting and usually is not taught explicitly. So, I will only finger or point that particular thing in this recording. So, there may be chances that you already know them or you have never heard that before. Sometimes I will try to ask a question with you, and if the answer directly clicks your mind, then you are ready for your CCNA. So, starting from the topic first, that is networking model, introduction to networking, introduction to TCP/IP networking. So, viewer, I want to make you aware that we have to study reference model so that there's something to be standardized about the network engineering in general, and we have to do rigorous study about different protocols, how they handle the data, how they handle the frame, what's their output data called. So first thing I want to make you all clear that every layer, not each of but every layer has its own set of protocols. So the topic had started from the reference model. Let's not delay and talk about the first two most famous reference model, the OSI model and TCP/IP model. To know the difference between of two, we have to understand how many layers do both have. So starting from OSI model, which have 7 layers. This 7th layer of the topmost layer is application layer. Then after that, presentation, session, transport, network and data link, and finally the last layer of the OSI model, or we can say the first layer, is physical layer. And if we combine the top 3 or the last 3, 7th, 6th and 5th layer of OSI model, we get a single application layer in TCP/IP model. The transport layers remains the same in both the models, while the network layer translated into internet layer, and the remaining 2 layers, the data link and physical layer, are both joined and called network access layer in the TCP/IP model. So the data have to travel across all the layers from a single computer and then way in reverse to another computer. And if the interaction of our data happens on the same computer, we call that adjacent layer interaction. For example, the 7th layer, that is application layer, wants to send some data. So the data have to be converted into electrical signals. So it have to travel all the way through 7th to the first layer, and the path taken by the data is called adjacent layer interaction. But when we relate something, for example the transport layer, that is TCP/IP, if a computer send a TCP packet or a IP packet, we refer the same IP packet to another computer, the receiving computer. We call it the same layer interaction. It always occurs in multiple computers. A good thing also know that a single layer defines the process, but the implementation of the layer on multiple devices is required to accomplish the function. And what we say to the adding up of information to the required sending of data, we often come across a term known as encapsulation. So the encapsulation is defined as the process of adding a header as well as a trailer, not in always but in front of data by a higher layer, and the removing of header or trailer from a data to get the actual data is called de-encapsulation. Or in terms of networking and in terms of OSI models and layering, the data at each layer is known as PDUs, that is protocol data unit. When the talk of the town is PDUs, Protocol Data Unit, we name some of them. Starting from the layer 0 PDU, we call them bits, while the layer 2 PDU is called as frame. Then we name the layer 3 PDU as packets, and finally the layer 4 PDU is called segments. The special name PDUs helps in context of talking about same layer interaction. Moving from that, now our discussion is about types of cables. So currently there exist three types of cable. The first normal cable, that is also known as straight through cable. The second cable is crossover cable, and the final cable that we are going to know is rollover cable. To understand how these all cables differ and what are the purpose of these different types of cable, we have to understand the wiring in them. So the very first generation of Ethernet cables have only two pairs of wire, means a total of four wires in them. So the pin 1 and 2 used to transmit the data, while pin 3 and 6 used to receive the data. I'm not sure, but there must be some spare pins. I don't know what they are used for, but all I have learned that the 1 and 2 are used for transmission, while 3 and 6 for receival of the data. So in that case, suppose 1 and 2 pins are connected to another 1 and 2 pins of the other end of the cable, and 3 and 6 are same connected with another 3 and 6 cable. The connection goes totally straight, and we call that straight through cable, while the crossover cable crosses over the wire of one node's transmission pin to the different pins used as receive pins on the other device. If I explicitly explain that pin 1 and 2, that is sending pin, connected to 3 and 6, that is receiving pin for the another device, but that will change in context, we will see further. But to continue, the third and sixth pins that is used for receiving is connected to first and second of the another end, and thus we get a crossover cable. And the strangest cable is rollover cable. To set the context of rollover cable, assume that we have four pairs of wire, that is a total of 8 wires numbered from 1 to 8, and on each side the one connected to 8, second connected to 7, third connected to 6, and if we connect all with their alternates, or we can say with their reverse number, we get a rollover cable. Now let's talk about their purpose. So the reason behind having so different types of cable, that there are different sort of device used in networking. Some device like our PCs or routers, even firewalls, specialize in sending data only. The main purpose, or the we can say the USP, or we can say the objective, is to send data. I know they can receive data, or what will they send if they don't receive anything? So bear with me. So the devices follow a separate type of category in which they specialize in sending data, and they send it on pin 1 and 2. And there is another category of device that main purpose is to receive, for example switch or bridge, not hub, because hub is a dumb kind of device, we will not use or talking about them here. So if the sending category of device sends data on pin and 1 or 2, and if switch also sends the data on pin 1 or 2, everyone is shouting, no one is listening, so none of the conversations happen. To make a conversation feasible, we have to use a straight through cable, but to change the mindset of the listening device, that to receive the data on pin 1 and 2 while send the data on 3 and 6, which ultimately goes to another first category of device, that is hearing or listening on pin 3 and 6, and thus the communication flows. And for the cases when we have to directly connect same category of devices with each other, suppose to connect a router with another router, a switch with another switch, a PC with another PC, and I'm sure many of you were curious what will happen if I connect the Ethernet port of my laptop or my computer with another computer? Will I able to send a file profile? Will I connect or control another computer with my own computer? I was one of the curious too. So today, after reading all this stuff, the answer is to connect the same category of device. We have to use a crossover cable. The cable makes up to the sending pins and receiving pins by alternating between two and making the communication possible. Now finally talk about the rollover cable. The use of rollover cable is very limited, and all I have heard that it is used to connect to the console port of some routers, mostly Cisco ones. We talk enough of wire, now the talk of the town is fiber, because everyone wants speed with low latency, and to fulfill these both requirements, what we get is fiber connection. There are two forms of fiber mainly, a multi-mode fiber or a single core fiber. Until now, as you can see, we are not going too much detail into any of the topic, but these things you have to know that the multi-mode fiber works with LED based transmitters, while the single mode work with laser based transmitters. It means that multi-mode fibers core, the part that transfer light signals from one end to another, is thicker, and by using LED in multi-mode fiber, they suffer from the long distance problem, while single mode fiber can travel to a far longer distance. But it also easy to repair or install a multi-mode cable than to use single mode. Talking of fiber connection, a thing that you must know that fiber connections also protect us from electronic interference. You must have read physics and stuff in which they talk about the passing electricity forms some kind of magnetic field around it. What will happen when we use electricity to send data? Obviously the electricity fields will occur, and electricity field pass out through the jacket used in wire, and there might be a possibility that someone might intercept the data while transmitting from these wires. By using the light based communication, we can also prevent that. So it is a plus point for fiber cables. Talking about the communication, in computer communication, it is possible to simultaneously receive or send data. The term we use to show this is duplex. A fun fact is that before the half or full duplex term, there was simplex communication. Apart from comedy shows, you have definitely seen TVs in which the only presenter will present some information. There is no way to send information to them directly. Not talking about the contact number and emails address they show. So that form of communication was known as simplex communication, in which only sender can send and there is no method of receiver to send back some information. Now after discussing the simplex communication, let's talk about half duplex. Ever heard of walkie-talkie? Which sounds something like this, in which one have to press a button to talk to the receiver, and all the receiver in the area listens, and when the prior sender says over, the other person starts talking. This is the true form of half duplex communication, in which the sender or the second sender has to wait to initiate communication after the first one finishes. And in modern communication, we experience the full duplex communication. We have option to send and receive, upload or download simultaneously. One fact more, that Wi-Fi operates always in half duplex mode. I will tell much of detail in future, so keep holding. So the half duplex mode is the core essence that we have to talk in the first few chapters, especially of Ethernet ones, in which we will talk about two of algorithms, which is CSMA CD and CSMA CA. The first one stands for Carrier sense multiple access collision detection, and the other one stands for carrier sense multiple access collision avoidance. So the CD one, the collision detection one, operate in Ethernet, which used to transfer in half duplex mode. Whenever there is a bump in signal, the network interface card senses that a collision has occurred in an Ethernet connection. So what happens in CSMA CD that it assigns a random timer to every node to resume communication, and having a random timer assures that no further collision will occur, and it happens as often as the next collision occurs. So that's why it is said that the LANs which have multiple computers in them are proved to be inefficient if there is a lot of traffic going on, because the collision ultimately slows down the network communication. And the CA version, the collision avoidance system, works in especially wireless mode, the Wi-Fi. As I have just told you that all the Wi-Fi communication happens in half duplex. To avoid collisions in Wi-Fi network, the algorithm uses multiple bands of frequencies to avoid transmission on the same path. Continuing from the topic, we have to talk about what's the point of presence in a network. Point of presence might be a physical network, or point of presence might be a physical location where two or more networks of communication device builds a connection from one place to the rest of internet. The more point of presence a network have, the more redundant it will become. Further, we are going to see how different protocols running on different devices helps to improve network redundancy. Your network provider that provides you with data connection to all over the internet is also termed as a point of presence. In this regard, there is a question. Suppose in layer 2, if a packet is encapsulated with HDLC layer or HDLC header, what will the router do to packet if the forwarding network uses Ethernet headers? The answer is that the router will strip off all the HDLC information from the data and re-encapsulate with Ethernet header, and the HDLC header will not use ever again. And this goes same for the other Ethernet to HDLC conversion as well. Now the time has come to discuss about the ARP, Address Resolution Protocol, and the table it maintains. So the Address Resolution Protocol is a communication protocol that used to discover link layer addresses. By the term link layer, we mean the second layer of the OSI model, data link layer, which deals with the MAC addresses. This protocol associates a layer 2 address with the layer 3 address. And there's also a term known as reverse ARP, which is exactly the reverse of the same, which relates IP addresses to MAC addresses. It actually maintains a list of devices which we call the ARP table, and most often people get confused between an ARP table and a MAC table. The difference lies in what kind of devices maintain those kind of table. For example, a layer 3 device, especially a router or a layer 3 multifunctional switch, maintains a ARP table. Actually, multi-layer switch maintains both a kind of tables, while a layer 2 device only, just like a normal plain old switch, maintains a MAC table. A MAC table lists the MAC address related to a specific port, while as we just discussed that the ARP table relates a MAC address to an IP address. There is also convention that says that the ARP layer, which contains the information of both layer 3 and layer 2, must have to be subjugated into a new layer of itself, calling layer 2.5, but we still don't have any specific name to that layer. Another most important point to be remembered that the MAC address table of a switch only gets flooded by the source address of the sender that uses a port on the switch to send some data. Please remember it that MAC address will not get flooded if the receiver provide a destination address, cause there's always a possibility that if the destination is not present on the port, the switch will simply broadcast it, and if it does not find any response, it will drop the packet. Now we are at the point of discussing the different types of MAC addresses and their contents. So a MAC address is a 48-bit field in which the half of the MAC address, which is 24-bit, the first 24 bits is called OUI, which stands for Organizational Unique Identifier. It identifies the brand that manufactures the network interface card, and it is also known as burned in address. Alternatively, we can also say that the out of 6-byte field, the first 3 bytes of a MAC address is called OUI, while the last 3 bytes are the device specific address and is must differ device per device. Now when the switch receives a frame that has a source and destination MAC, the switch puts the source MAC in its MAC address table and forwards it to the destination, which is again listed on the MAC address table specified on a specific port. There is also something called broadcast MAC address. It is nothing different, but as we know that MAC address consists of hexadecimal characters, so the maximum of hexadecimal values are F. So the 6 bytes of F is called the broadcast address. A MAC address that contains all characters as F is a broadcast address. So when a switch receives a broadcast address, it means that it does not have a specific forwarding direction. So the packets that have a forwarding direction is called unicast address, while the addresses with F's in it is called broadcast address. So a switch forwards broadcast address to all of its ports except the one on which it receives. It is one of the most important thing that you have to know, as I have given tens or hundreds of mock test paper, and this specific question arises in almost each of them. If there are frequent forwarding of packets, it will consume the precious bandwidth. So what are our options to limit this non-required activity? And it's also very clear that the more switches we add to the network, the larger the broadcast domain it will be, and further the network will be congested. So what are our options? A first class option is to use VLAN, Virtual Local Area Network. The term virtual means that despite of physical connection to a single switch, we divide this group of devices to limit their broadcasting to a specific sets of device. It helps us to preserve the bandwidth and often with security. So let's explore this VLAN in much slightly more detail. VLANs can be created on any switch, and to include some switch or devices on a VLAN, we have to tie a specified port which connects to that specific device within a VLAN. And to propagate the VLAN itself, we use the VTP, VLAN Trunking Protocol. VLAN Trunking Protocol is the Cisco proprietary protocol that used to maintain the consistency of VLANs within a network. The VLAN Trunking Protocol operates in 3 modes. First is server mode, second is client mode, and the third is transparent mode. By default, the VLAN Trunking Protocol server operates. By default, the VLAN Trunking Protocol operates in the server mode, which allows to create, add or delete the VLANs. While to limit the administrative capability, we can also change the VTP mode to a client mode. While the VTP transparent mode has a unique purpose only to be used when we don't want a switch to be a part of VLAN, but to be act as bridge between transferring the VLAN information from one part of a network to another. We can say that in just like in chemistry, some chemicals that helps to increase the rate of reaction of some another thing by not taking part in it, we call that a catalyst. Just like that, the transparent mode act as a catalyst, acting as a bridge between two networks to transfer VTP informations while not being part of that. To keep track of VTP information and their updates, switches maintain something called as revision number. The higher the revision number, the latest the VTP information is. So a precautionary step is to be shared that while adding a switch to a network, especially a old switch, we must have to reset its revision number so that it not interrupt the already working of the defined switch already present in network. You can reset revision number of a VTP by changing the domain to a non-use domain or by setting the switch into transparent mode. Some more interesting things to know about VLANs, that is there are VLANs ranging from 0 to 4095, that is 4095 VLANs, out of which the VLAN number 1 is the default VLAN on a Cisco switch. The default VLAN is the VLAN in which all the switch turns into a member just after the initial boot up of the switch, while the first, the VLAN 0, and the last, VLAN 4095, are for the system use and cannot be assigned for any use. VLAN number 1002, 1003, 1004 up to 1005 are the Cisco defaults for FDDI and token ring. FDDI stands for Fiber Distributed Data Interface. We will talk about these in future, but right now the point is that these specified VLANs also cannot be used, and the range extending after 1006 up to 4094 are called the extended VLAN range. We emphasize the term extended as some older switch does not support these numbers of VLAN. So if the question states that a switch is particularly old, we have to be aware of using these named VLANs. Now another thing is to know that there is also something called a native VLAN, which will play a role after we understand that how the switch ports operate. So let's clear that first. A switch port operates either in access or the trunk port. The access port defines that the switch is used to carry data traffic for something specific, a device, while the trunk mode states that the switch port is used multiple signals simultaneously, which means it can contain the data of multiple VLANs or of an entirely different network. Talking of trunk port, the data must have to be identified by some form of technique that defines to what VLAN does it become, to what VLAN does it belongs. To do so, Ethernet header, or you can say the network header, adds a special VLAN identifier, or we can say a VLAN tag. So the trunk port transfers the tagged data from one place to another after a switch processes it and send it to the required end host, which is obviously an access port, and the access port does not or cannot transfer the tagged data. So the switch has to make the decisions to what to do with that particular frame. And moving from all back to the native VLAN. A native VLAN is a special VLAN whose traffic travels on the same trunk port without any VLAN tag. It is a good practice to make the same VLAN as the native VLAN in all switches of a network. Otherwise, it will lead to VLAN leaking. By understanding VLAN leaking, I am sure that you will properly understand the purpose of native VLAN. So, the VLAN leaking refers to the situation where frames from one VLAN unintentionally leak into another VLAN. Mostly it is a case of mismatched native VLAN. We have to manually set a native VLAN on each switch. The best practice is to set to a non-used VLAN as a native VLAN. But for example, if a switch A has native VLAN 10 and switch B has a native VLAN 20, as we have already discussed, the native VLAN does not tag the traffic. So, the frames traveling from switch A to switch B specified for VLAN 10 may drop or leak into VLAN 20 of the switch B because they are not tagged, or vice versa. It reverse can happen, that the frames from switch B can leak into the switch A's VLAN 10. And I hope I am making it clear.